Good afternoon, everyone, and welcome back to the International Conference on Frontiers in Industrial Biotechnology, hosted by the Department of Biotechnology from St. Joseph's College of Engineering. As stated earlier, please do not introduce yourselves in the chat box and keep your microphones on mute. And if you face any technical difficulties at any point, relay them in the chat box and we will look into it. I now call upon our coordinator, Ms. Kalavati G, to give the welcome address.
Hello and good afternoon, everyone. It is a great pleasure for me to welcome you all to the session 3 of AICT sponsored International e-conference on Frontiers in Industrial Biotechnology, hosted by the Department of Biotechnology, St. Joseph's College of Engineering. It is indeed a great pleasure for me to welcome the speaker of today's session and all participants, including faculties, entrepreneurs, research scholars, and students. And once again, I'm glad to welcome the distinguished speaker, Dr. Jose Antonio Teixeira, Professor, Biological Engineering Department, University of Minho, Portugal. You're welcome, sir. Now I request Ms. Vatika to introduce the speaker.
Thank you, ma'am. I have the great pleasure of introducing the guest speaker for this event, Dr. Jose Antonio Teixeira. Dr. Jose Teixeira is a professor in biological department at University of Minho in Braga, Portugal, and president of the Scientific Council of Portugal Foods, which is the largest Portuguese food cluster. He has a degree in chemical engineering from the University of Porto and obtained his PhD in chemical engineering from the same university. He is also a member of the Scientific Steering Committee, for which he was the previous head of the Research Unit Center of Biological Engineering and has served as the president of the Portuguese Biotechnology Society since 2009. He is also a member of the Institute of Food Technologists. Dr. Teixeira has a wide research experience in industrial and food biotechnology with over 500 publications in these topics. He has edited 6 books and published more than 550 papers in peer-reviewed journals and has an H index of 70 for Scopus and ISI. He was named the highly cited researcher in 2018 and 2019. His work has been widely recognized and he has received the Stimulus to Excellence in 2006, which was given to him from the Ministry of Science and Technology in Portugal, and he was also the recipient of Scientific Merit Award from the University of Minho in 2015. So it gives us an immense pleasure to have you with us today. I request you to take over the session.
Okay. Good morning, everyone. I think it's good afternoon in India, but here in Portugal is good morning, everyone. Thank you for inviting me to make this presentation. I hope everyone is listening to me correctly. Really, this is a very, as I said, it's a very strange situation not to be really facing people that are listening to my presentation. But anyway, I'll do my best so that this can become an interesting session. As I said, thank you for the invitation. It's quite a pleasure to make this presentation, and I would be better if I could be in India, but anyway, it's life and we have to move ahead. So my presentation is, as you can see, clean technologies for the production of chemicals, the use of moderate electric fields. As a matter of fact, I decided to focus this presentation on electric fields or moderate electric fields, as it is a subject that we have started to consider a few years ago for another specific applications, in particular for the food industry. But with the knowledge we got in the meanwhile, we decided to use this for extraction of bioactive compounds from lignocellulosic materials, okay? And that's why I decided to give some information on the work we have been doing on the use of these moderate electric fields. Anyway, just a small map of Portugal. As you can see here, we are in north of Portugal, here in Braga. Obviously, it would be a great pleasure to have you all visit in Portugal, and in particular Braga. Braga is a very old town and has also nice surroundings. So if you want to spend some time here, please visit us whenever you can, okay? And I hope that can happen soon. As I said, I work at the Center of Biological Engineering, and this is my research group. And as you can see here, We have a main frame that is fractionation from the materials from different sources, from, as you see here, valorization of natural resources and wastes. And we develop all the fractionation line to obtain different products. Obviously, related with that, we have worked on the developing of what we call cell factory and also development of new types of bioreactors. And we are very much focused on what we call oscillatory flow reactors and continuous processing. All this work is also linked with the work we have been developing on the use of on the food technology, and in particular on the use of added value compounds that can be extracted from different sources, in particular lignocellulosic materials. Okay, so the presentation will be divided, let's say, in these 5 main sections: introduction, strategies for valorization of lignocellulosic materials, some considerations on LSM's pretreatments, and I'll focus a little on organosolv and autohydrolysis processes, and then I'll give some examples of what we consider relevant on the use of moderate electric fields for the extraction of added value compounds from lignocellulosic materials, and some very fast conclusions, very simple conclusion. Okay. Obviously, nowadays, everyone talks about circular economy because it has been recognized that circular economy has potential to help us make better decisions about resource use, design, and waste, and provide added value for business and develop secure routes for different environmental sustainable applications. Okay, this is quite important for future generations. And this also comes up with another relevant issue that has to do with the amount of waste that are produced by the food chain. This set of data shows that we produce huge amounts of food wastes, and that's not a good idea. So we need to develop technologies to recover these food wastes and introduce them in this concept of circular economy. As you can see here, we more or less waste 1/3 of food production. So we have to find ways to get most of these wastes in the global production chain and recover them. You can see here that you have huge amounts of food wastes, and lots of them are lignocellulosic materials. Not all of them, but most of them are lignocellulosic materials, and we have to find ways to add value to this. Also, you can see here that, and although the figure is not very clear, there's a trend on the change of the use of different resources, and wastes are becoming more and more important, and within a couple of years, waste will really be important for the production of several materials. Next. Yeah, it's slow, but... Okay, that's what I think I was in this slide. So you can go on. Next. 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 And next. Okay. Okay, I was talking about circular economy and about just let me changing from the traditional, and then I started to discuss some ways of using biomass. And the idea is obviously to go from the traditional traditional refinery to a biorefinery, where the starting material is the biomass, typically low-value biomass that will be used instead of oil as a raw material for the production of several materials, as you can see here. So in the end, what we are expected to have is value-added products from biomass, replacing products we can typically obtain nowadays from oil. That's what's shown in this scheme. So please move to the next one. And okay, this scheme is a little hard to see, but basically the idea is to show the main constituents of biomass, and that will be really the starting point for most of the products we can obtain from biomass. So we have typically starch from cereals, but then we have lignocellulosic materials that are mainly constituted of hemicellulose, cellulose, and lignin, and then we can have some oil and some other proteins. But anyway, these are the main starting materials that will give rise to the intermediate platforms that we further use to develop building blocks that be then transformed to several chemicals. Okay, and this is the concept. And next slide, please. If you see here, we can talk really of different types of biomass according to the way they are processed. So we have what we call first generation biomass, typically starchy materials and materials from sugarcane that are quite easy to transform into materials that can be easily transformed. Then we have lignocellulosic biomass that we call second generation feedstocks. And then we can have third generation and fourth generation. And third generation, we can also have algae and macroalgae. And then in fourth generation, really other types of material, including CO2 and as starting material. Okay, please, next. So if we look overall to what we can consider, and if you look to the bioresources we have available, and the focus on agro-food waste and biomass wastes, basically what we can do is look at their composition, and remembering that, okay, as I said, we have typically on these materials that most of them, but not all of them, are lignocellulosic materials. We can have typically 1/3 of the three main compounds, cellulose, hemicellulose, and lignin. But apart from that, we have other compounds that can be extracted and that can also be present in high concentrations. So basically what we can do is to extract some compounds before going to the more hard and harsh treatments to separate and fractionate cellulose, hemicellulose, and lignin. And so from that, I would say that we can really have a first separation strategy for the compounds that do not need to be so hardly processed as it is the case of cellulose, hemicellulose, and lignin. So, and this is really what the scheme shows, that in a first step, we can really recover by very simple treatments these compounds, like biocompounds, including antioxidants. And so, sorry for this small interruption. So we have to develop pre-treatments that have to follow these lines presented here. They have to be simple and economical. They must comply with limited requirements of energy, processed water, and chemicals, limited corrosion to the equipments, ability to alter the structure of lignocellulosic materials and to extract the compounds of interest. They have to be selective. And in the end, we need to recover everything that is present there in an added value mode. And obviously, in the end, we don't want to generate lots of wastes. So please, next. Typically, when you see literature, what you can find is several approaches, or two main approaches to deal with these lignocellulosic materials. So where you have quite interesting as green processing, the others maybe a little more aggressive, not all of them. Or obviously, in the end, you can make use of combined or mixed methods to make use of this. Okay, so next slide, please. This is a list of materials we have been on. Eucalypts, that we also produce large amounts of eucalypts, and other materials that are quite available. Pine bark, for instance, and more recently, we have been focusing on our work on the valorization of seaweeds because of the high the coast we have here in Portugal, it can be quite an interesting source of seaweed for further use. And then we've been working, as I said, with different pretreatments like autohydrolysis, organosolve, and then acid and alkali pretreatment, some lime pretreatment, and also with ohmic heating. And I'll come back within a few moments to the ohmic heating issue because, as I said, case study I'm going to detail a little more. And from that, we can have different compounds, and we've been focusing on these different compounds. Obviously, we get in percent fermentable sugars. From there, we can go to bioethanol and other compounds. Really, bioethanol has been the focus of our research for several years now. We can also have xylo-oligosaccharides because of the importance they are having nowadays as a prebiotic. And then we work with phenolic compounds, with lignin as a source of antioxidants and other structures to be used in several applications. And obviously, we can also do some work on enzyme enzymes production from these lignocellulosic materials for further use in the process of extraction of the lignocellulosic materials and processing of lignocellulosic materials. And we've been producing also some cellulose nanocrystals because it's another way to add value to these less lignocellulosic materials. So next slide, please. So as I said, I think that, and we've been doing some work on this, autohydrolysis and organosolve pretreatments are quite interesting ways to deal with this. So in autohydrolysis, what we really have is water as a solvent that in a pressurized reactor is, let's say, processed at so it's processed at a high temperature, around 200 degrees centigrade, depends on the material to be processed and the optimization conditions that have to be carried out. But from that, you have a liquid phase where most of the oligosaccharides are present, okay? And a solid phase where you have the cellulose-enriched phase and most of the lignin, okay? And so really what you do, you separate these two phases, okay? One liquid phase is where you have the oligosaccharides, and you can also have some degradation compounds like furfural and HMF, and also some phenolic compounds, and I'll come back to these phenolic compounds later. And then you have solid phase, where that can be further processed by enzymatic hydrolysis, for instance, to hydrolyze cellulose and separate the lignin, okay? The main advantage that are associated with this technique are that as you are using water, corrosion is not an issue. You don't have sludge being formed, and cellulose is not degraded, meaning that the whole cellulose can be fully used, and the process is simple in the capital and operational costs related with this process are quite simple. I think this is an interesting alternative to be considered. And the other one, as I said, is organosolve. So please, next slide. And in the organosolve, as I said, the advantages are also relevant. It's a sulfur-free process. You can even recycle some reagents, like if you use glycerol, you can even recycle that. You can have a selective delignification, okay? And you can use, for instance, to this organosolve process, glycerol, that is a byproduct readily available from the biodiesel industry. Obviously, you can use other products like ethanol, for instance, or methanol, but glycerol is an interesting alternative. And so in this case, where you also have a pressurized reactor, the phases you get after processing in the reactor are quite different. In the one phase, you got liquid phase, you get what you call the black liquor, where you have most of the lignin and MS-loss derived compounds and some phenolics, and the solid phase, where you have most of the cellulose that can be further processed, okay? As you can see, basically, there's a difference in the properties of phases that are obtained here in comparison what you get with the autohydrolysis process. And every situation has to be evaluated considering the final and target product. Next, please. Just a simple scheme, as I said, we've been working on bioethanol for several years, and when you look at lignocellulosic biomass, this is really what you want in the end. You want to have a really consolidated process where in just one vessel, let's say, you have the hydrolysis and the fermentation, okay? And when we talk about fermentation, we talk obviously about fermentation of both C5 and C6 sugars to bioethanol. Okay, this is not straightforward. As I remember that ethanol or bioethanol has been an issue for more than 50 years. And we are moving ahead, but not enough yet to make this a very interesting solution overall, to have the overall integrated solution. Because, okay, when you make pretreatments, you can have inhibitors being formed that can limit the activity of cells. And you can really have problems with stress on cells when you make hydrolysis and simultaneous saccharification and fermentation. Apart from that, and this is relevant because the hydrolysis temperature is not the same as fermentation temperature, and this can create some thermal stress to the cells. Apart from that, it's not easy to have C5 and C6 sugars being fermented at the same time. And for instance, there can have also inhibition problems of the enzymes when hydrolysis is being developed. Okay, so next slide, please. If you see overall the process for the production of bioethanol or whatever, I'm talking about bioethanol because it's a subject we've been working with, but this can be really applied to several other chemicals. You can have, as I said, as a eco-friendly treatment, you can have hydrothermal treatment, and the advantages, as I pointed out, are no corrosion, no sludge being formed, no cellulose degradation, and low cost and operational costs. And when you get the slurry with high solids loading, and that's really what you want, to have the more concentrated possible slurry to reduce the operation costs, okay? You can have here really very important problems concerning related with mixing in this part of the process, okay? And then you go to the simultaneous saccharification and the fermentation process, where also you want to have high biomass concentrations and high enzyme loads, and there you can have really relevant challenges related to mass and heat transfer, and also, as I said before, problems related with the enzymatic action and with the activity of cells, because you can have stress induced to cells due to different temperatures that are needed for saccharification and fermentation. And obviously, you can also consider other issues like nutrients deficiency and so on. Really, there's still a lot of work to be done on this topic of integrating the processing of biomass for fermentation and production of chemicals. So next, please. Okay, so going a little back again to lignocellulosic materials and seeing what we need to do to have a nice process and a friendly process, we need to introduce green and chemistry and engineering concepts for the use of for the processing of these lignocellulosic materials. So overall, and I've been saying this since the beginning of this talk, we need to maximize resource efficiency, to eliminate and minimize hazards and pollution, and design systems holistically and use life cycle thinking. So this is fundamental to have a sustainable process for the valorization of lignocellulosic material. Really, this applies for almost all situations. So next, please. So there are several principles that need to be applied, what we call green principles or green extraction principles. Principle one, innovation by selection of varieties and use of renewable plant resources. And these principles can be applied to the extraction of natural products. So you can have innovation by selection of varieties and use of renewable plant resources. Use of alternative solvents and principally water or agro solvents, so meaning that we don't want pollution and water is really the best solution. Obviously, we need to reduce the water consumption. Another relevant principle is that we must reduce energy consumption by energy recovery and using innovative technologies. We must look at things like production of co-products instead of waste to include the bio and agro-refining industry. Reduce unity operations, and with this can be done, for instance, by integrating different unit operations, and favor safe, robust, and controlled processes, and aim for a non-denatured and biodegradable extract without contaminants. So these are very, I'd say, common sense principles that we can apply if you want to consider the green extraction of natural compounds. So next, please. So we need to reduce energy consumption overall, reduce energy consumption, reagent solvents consumption, minimize waste generation, and minimize operation time, and to improve overall yield, selectivity, and quality of the extract. And so we need to shift from conventional organic solvent-based process to novel zero waste processes, okay? So next, please. So when you talk about extraction of bioactive compounds, and I'm going to address now that part that is not cellulose, hemicellulose, lignin. We want to extract the other compounds that are there. So when you consider these extraction processes, we have traditional ways to do this. So we must choose the right solvent to be used, okay, and typically, as it's written here, we can use solid liquid extraction, or we will use in principle solid liquid extraction. And so we have to select the target, the solvent to be used, and this has to be targeted, let's say, to the compound that we want to isolate or to separate. So, and we have to consider relevant properties like polarity, hydrophobicity of solvents, and for that we've been using solvents like dichloromethane, ethanol, methanol, water. We can use each or not, so in most of the cases we need to heat our system to enhance the extraction, and obviously we use agitation, okay, and by that we can increase solubility and also increase mass transfer and accelerate the extraction process. Okay, next please. So the objectives, as common sense says, is that we want to have high extraction yields, high concentration of the target compound, and minimal damage of this target compound. And so, as I said before, we need to consider the polarity of the target compound, the molecular affinity between solvent and solid, mass transfer issues, use of co-solvent, safety, toxicity, and obviously, in the end, feasibility, and particular financial feasibility. Okay, next, please. And there are lots of techniques that have been developed recently for the extraction technologies to be used in this process, okay? So we have accelerated solvent extraction, subcritical water extraction. In a way, autohydrolysis is almost subcritical water extraction. Microwave has been quite developed in these last couple of times. Ultrasounds, pulse electric fields, electric heating, use of other solvents like ionic liquids and dipotectic solvents, okay? Also supercritical fluid extraction, and other techniques like enzyme digestion, extraction, and mixed approaches. So we have a wide set of technologies to be used, and we have to select the best one considering the principles I've mentioned before. Next, please. And as I said, my focus, or the focus of the work that I will present in a few moments, is about electric fields application, about the use of electric fields, okay? And here in this figure, you can see here the different types of electric fields that you can be used, okay? You can have very high energy electric fields and with high intensity electric fields. And you can have, as it's here, it's said here, post-electric fields, high voltage electric discharges, pulse ohmic heating, moderate electric fields, and ohmic heating, okay? And really, we have been interested on this part of the graph, okay? On the ohmic heating, let's say, topic, okay? And why are we interested in this ohmic heating topic, okay? Where we apply a lower intensity electric field. But we are interested in this for a very simple reason. Although there have been reports for medical application of high intensity electric fields, we decided to focus on this one because really when we started this, we started to study ohmic heating as an application for food pasteurization and food sterilization, okay? And so with knowledge we got on the use of these electric fields, we decided to develop or to apply electric fields on other on other situations. And for that, we started to work on electric fields as an extraction technology, okay? As I said before, electric fields have been used on food processing because they enhance the food quality attributes, and I'll explain why this is happening. They can improve the process efficiency, reduce spoilage agents more effectively than some, let's say, traditional heat exchange based processes, and they can also, as I said, and that's our target, enhance the extraction yield and selectivity. And in the end, they can improve the process's sustainability due to the costs associated with their operation, okay? So, because we knew a lot about electric fields for food processing, we decided to go for the use of electric fields, in particular ohmic heating, for the valorization of bioresources as a technology to enhance the extraction of valuable compounds from lignocellulosic materials compared to traditional extraction technologies. Okay, next please. So, electric heating, ohmic heating, Joule heating are all different ways of saying the same. And this has to do with the Joule effect. So, in this case, ohmic heating is a process where an electric current passes through materials with primary heating, objective heating them. So, there's electric current passing through the materials, okay? Heating is generated inside the material to be heated, okay? So, the heating process does not depend on heat transfer between phases and interfaces, allowing uniform heating and extremely fast heating rate. And this is really a relevant advantage when compared to traditional extraction and heating process, because heating and mass transfer issues in principle are not relevant, okay? It also allows for heating of large particles and viscous fluids at comparable rates as long as their conductivity remains similar, okay? And apart from that, and complementary to this, ohmic heating has also an effect on cell wall permeabilization, okay? And this has been used for other electric field-based process also. So when considering ohmic heating, what are the temperatures that we have to evaluate? Temperature, processing temperature, obviously, the type of solvent that is being used. Typically, we have been working with water and water ethanol. That water is a very different solvent, and that is also used for food processing. And the properties of electric field, and when considering the properties of the electric field, we have to consider the distance between the electrodes, the voltage, and the frequency of the electric field being applied. And obviously, like in any other process, extraction process, complementary to temperature and solvent, we have to consider the time, solvent to solids ratio, and stirring intensity. Next, please. So as I said, electric ohmic heating has these advantages: as a fast and uniform heating, in principle lower energy consumption, higher recoveries, low solvent consumption, shorter extraction times, and higher selectivity. And that's what we are trying to demonstrate. Okay, next. So basically what we have here is a synergy between electrical field application and the thermal effect, okay? And then in the end, we can have extraction through an efficient and clean label approach, okay? And so this is also can be also applied because biological materials are typically good electrical conductors, and then by this I mean that we can apply the electric field and transmit let's say the electric field throughout the entire material. Okay, next please. Okay, and now I'm going to present 2 or 3 cases of the work we've been doing on this ohmic heating for the extraction of different compounds. Okay, this is one of the first works we did on this. It was to evaluate the application of ohmic heating on the extraction of food-grade phytochemicals from colored potato. Okay, and really what you can see here is that, so in this graph you have the plot of temperature versus time. Okay, you have one situation where you have conventional heating with a certain temperature profile, okay, and then you use ohmic heating by with the same temperature profile, so that you can compare the electrical field effect, okay. And then you have another alternative that's shown here in this line, okay, where you have, let's say, an instantaneous ohmic and a high intensity field application. Okay, you can see here that we call it this moderate electric field, instantaneous. So it can go up to 100 degrees in just 1 second, okay, by applying an electric field by 200 volts per centimeter, okay. And then what we did, really, we had these 3 situations, okay, and we decided to evaluate the effects, how these 2 situations act on the extraction of these phytochemicals from colored potato, okay, and we did this in water. Okay, next, please. Okay, here you have those different situations, then treated process. I'll say we did a blanching process, and then we did the extraction, and okay, and you can here see the 4 situations without any treatment: the conventional treatment, moderate electric field, and instantaneous moderate electric field. Also, that situation where you have a sudden rise in temperature up to 100 degrees. Okay, and really what you can see is that the amount of extraction, or the extraction yield of anthocyanins, that's the colored compound that we target to, is much higher when you use the MEF instantaneous, and is also overall higher than used conventional processing technology. Okay, next. And interestingly, also, the rate of extraction, the kinetics of the extraction were favored when you were using the instantaneous process. And also the ohmic heating-based process allowed for larger amounts of anthocyanins being extracted, but also the rate of extraction was faster. So, meaning that really you have this data suggests that ohmic heating can be an interesting alternative for the extraction of these bioactive compounds from different materials in comparison with traditional extraction techniques. Okay. We also can see, in next slide, please, that the energy efficiency of the process is very much improved when you use ohmic heating compared to the traditional heating process. Okay, You can see here that this is the amount of energy you spend. And you can see here that, okay, there's a big error bar here. But anyway, you can see that there is a significant reduction in the extraction cost of the energy consumption for extraction when you compare ohmic heating with conventional heating, and that can also be a relevant issue. Okay, next, please. And we can also see that ohmic heating acts by inducing rupture of cell walls. Okay, you can see here the extraction when no ohmic heating is applied, so when no electric field is applied. And here you can see situations you have a 20 volt per centimeter field intensity, and where you apply that 100 volt per centimeter instantaneous process. And you can really see here that there is a strong rupture of cell walls, and that's the effect of the electric field being applied. Okay, and this overall helps on the efficiency of the extraction process. Next, please. Another material we've been working with is this extraction of bioactive compounds from wine-making residues. Okay, why are we interested in wine? For a very, very, very simple reason. We produce and drink, sometimes unfortunately, a lot of wine. So, and we have big amounts of wastes being obtained from the wine industry. Okay, and among these wastes, we have several types of waste, but here I'm focusing here on the grape skin that is wasted after the extraction of the juice to be further fermented. Okay, and what I'm showing here is the extraction of colored compounds from these materials. Okay, and we have here two types of skins, but overall the wine grape skins, but overall the results are similar. You can have dried grape skin and fresh grape skin, but the relevant thing is that you can see that the amount of this colored compound being extracted is quite different according to the treatment being carried out. Okay, and the treatments that are carried out are those shown here. Okay, here you have the traditional and conventional, let's say the conventional extraction process. Here you have the electric or the ohmic heating process. Okay, by applying a field intensity of 60 volt per centimeter. Okay, and doing the extraction at 40 degrees for, let's say, 1 minute, and then you have this where you apply a high intensity electric field. Okay, that allows you the electric field intensity is the same, but you don't control the temperature here, so you can go up to a higher temperature, around almost 100 degrees. Okay, what you can see here is that, and really the visual information is quite obvious, is that when you apply ohmic heating, really the amount of these colored compounds you get is much higher when compared to the traditional extraction process. Okay, and by this situation where you allow for a higher temperature as expected, the effect is even more obvious. Next, please. And here you can see again basically the same presentation. Unheated system, controlled at 40 degrees centigrade for 1 minute, so without ohmic heating. When you apply 60 volts per centimeter, and you keep the temperaure at 40 degrees for 1 minute, and you go up to 100 degrees centigrade, and you do the extraction just 1 second. You can see here really that there is an obvious difference between the amount of colored compounds extracted. Okay, next, please. Sorry, I was going to press my key. Okay, another material we've been working with, and this was in frame of a European project, was the use of this ohmic heating, or as you may call it, moderate electric fields, as a potential tool for sustainable recovery of phenolic compounds from Pinus spinaceae bark. It's a widely available plant here in Portugal, and so there are lots of wastes being produced, and really we decided to evaluate if ohmic heating was really efficient on the extraction of these compounds. Okay, and what we did was, let's say, quite simple. We used ohmic heating and conventional heating, and also evaluated the effect of two solvents, water and ethanol, or let's say mixtures of ethanol in water. Okay, and we evaluated the yield of extraction of these phenolic compounds, the phenolic compound, a relevant property that is the antioxidant activity. Okay, and that you further also analyze different phenolic compounds that were being obtained. Okay, and in the end, as before, we calculated the energy consumption associated or linked with this ohmic heating process. Okay, next, please. So what you see here is the extraction yield, okay, and the total phenolic compounds being obtained. Okay, as you can see here, okay, you can see here you have ethanol, a mixture of ethanol and water, 50% of ethanol and water, and here you just have water, and here you have, okay, same situations. Okay, but really interestingly is, first of all, you can really see that ohmic heating induces a larger extraction than conventional system, okay, regardless of the solvent being used, okay. But more interestingly, when you look at the total phenolic compounds being extracted, it seems that there is a selectivity effect associated with the application of ohmic heating when you use the mixture of ethanol and water as solvent. Okay, this can be interesting, and I think that we can explore further this as a technique to increase selectivity of the extraction process. Anyway, relevant information is that ohmic heating is more effective in the extraction of overall extraction yield, but can also help on selectivity of compounds being extracted from this pine bark, okay, pine wood bark. Okay, next, please. As I said, we also measure the antioxidant activity, and as you can see, you use the three traditional techniques, FRAP, METS, and EPPH as techniques, and you can see really here once again that ohmic heating really is more effective than conventional heating. And it's interestingly the increase in this antioxidant activity, the values presented also show that there is a certain selectivity because the increase in the antioxidant activity depends on technique that is being used for the measuring this activity. Okay, and here you can see really how the ohmic heating acts on structured material being processed to enhance the extraction. And once again, we have an effect on cell walls. Next, please. So to conclude this work, we can see that, or just a brief conclusion, this is that there is an improved overall extraction of antioxidant compounds on this by using ohmic heating. There is an enhanced extraction selectivity when mixtures of water and ethanol are being used. And obviously, the target of all this is to use these high bioactive extracts for further applications, in particular in the food industry, where they can be used as ingredients in functional foods or be incorporated in edible packagings and coatings, for instance. Interestingly, as I said, as I've been pointing out, is that the consumption, the material, the energy consumption in the process, it's much more interesting when ohmic heating is being used than the traditional conversion process. Okay, so it's really a big advantage of this ohmic heating that is being used to enhance the extraction of bioactive compounds, and as I said, can be the first step in the extraction of materials from, for instance, lignocellulosic materials, and then we can proceed later for processing of cellulose, methicellose, and lignin. Next, please. Okay, another material, now I'll stop in 5 minutes. Another material that we have been working with, as I said, and because of the interest we have in Portuguese coast, is the study of is the use of macroalgae as a source of different materials to be developed in this biorefinery concept. Okay, macroalgae are not lignocellulosic materials, but are a quite interesting material to be considered in this concept of biorefinery and development and use of sustainable technologies and materials. Okay, so we have been working with several types of algae. By the way, this figure shows our device. Let's say the ohmic heating is there. You see this white thing here. There you have an electrode here and the other electrode, okay? And by using this device, you can control the frequency and the intensity of the electric field you apply, okay? And then you can monitor all the relevant data, in particular temperature of the process here in this monitor, okay? But what I'm saying is that our target is to use macroalgae as an interesting start material for the obtention of different types of compounds. We have been working with different type of algae, but due to the economic importance for the Portuguese coast, we have been working with the Gracilaria vermiculophylla, a red algae. Okay, and what we did was to once again apply ohmic heating and evaluate the effect of ohmic heating on the extraction of different compounds using different water ethanol mixtures and a solid liquid ratio of 1:30. Okay, this has still to be optimized. Okay, and we also use two different extraction times, 1 and 2 hours, and the target was to compare ohmic heating with conventional water bath using the same temperature, okay, same temperature profile. And in the end, what we evaluated was the extraction of the overall extraction yield, the extraction of carbohydrates, and also if the ohmic heating process had some effect on gel strength of material that was to be obtained after extraction, because carbohydrates are relevant, as the carbohydrates extracted from this algae are relevant to be used in gels, on the protein extraction, on the extraction of total phenolic compounds and pigments, and also related with this on antioxidant activity. Okay, and next, please. As you can see here, when you look at the carbohydrate content, there's a 20 to 30% increase in the extraction of carbohydrates after 2 hours. On protein content, also the same. And interestingly, the gelling ability is not very much affected when you use ohmic heating. Okay. Next, please. We also evaluate, as I said, the extraction of the chlorophylls, carotenoids, phenolics, and also evaluated the FRAP radical scavenging activity. And in all the situations, ohmic heating shows that there is a clear effect of the use of this ohmic heating technology on the processing for the extraction of different compounds from these macroalgae, meaning that this can be really an interesting alternative. Next, please. So overall, on this macroalgae case, we observed that concerning yield, difference in yield was generally not significant except for water extracts. Carbohydrate contents and gel strength were more than 20% higher than for ohmic heating, in particular case of water. And I must remember or highlight that this efficiency or increase in efficiency depends on the solvent that is being used. Concerning protein, ohmic heating was more efficient than conventional extraction at 1 hour of extraction, when also water was used. Ohmic heating was more efficient than 2 hours of extraction, using this case a mixture of ethanol and water. And ohmic heating displayed a higher increase of pigments, corroborating the antioxidant activity, especially with 25% of water. This means that, as expected, as I said, this efficiency depends on the solvent being used, and this requires an optimization on a case-to-case or target product basis. Okay, so concluding, ohmic heating is an interesting alternative with reduced energy consumption and improved extraction performances that can be used to recover functional ingredients or additives from seaweeds for the food industry. Important selective effects are present for specific compounds, families, solvents, extraction times combinations. Okay, so we must optimize all and integrate all this extraction process. Okay, next, please. And another case we've been working with was the recovery of phycocyanin from spirulina, in this case a microalgae, because phycocyanin is a very valuable compound. And once again, here we can see that we have much better results when you use ohmic heating than compared to conventional heating. Okay, next, please. And I think it's one of the last ones. So be green, sustainable, and socially responsible, and consider ohmic heating as an interesting alternative to be validated in a case-by-case basis. Next, please. And these are some of the people that are working with us on this processing. Most of the cases, ladies, but that's the team we have at the moment. And thank you very much for your presentation. I hope you have enjoyed it. Thank you.
Thank you very much, sir. It was an informative presentation. We just have one question for you here. So
Sure.
I'll read it out to you, sir. It's asked from someone, we're streaming it on YouTube, so it's from there. What chemicals can be extracted using this method, and which one will be the most effective?
No, so problem, what chemicals can be, the important thing to use this technique is that you must guarantee a certain conductivity, okay? And sometimes you need to add salt to increase the conductivity of materials being extracted, okay? That's not the case of these situations because all these materials are conductive. But in some situations, we need to use salt. Potentially, you can extract anything that can do with other extraction technologies, okay? But if you go for a conventional extraction, the only difference between conventional extraction and this ohmic heating is that you add an extra effect by adding the electric field effect, okay? And also there's a heating effect. But in principle, you can use this universally for any product you'd like to consider.
Yeah, so that's it, sir. We don't have any other questions, sir. Thank you very much, sir. The presentation was really informative, and we learned a lot about LCMs and how doing using green extractions and doing it in a clean way. We learned a lot. Also, thank you for being patient and understanding throughout the technical difficulties at the start, sir. Thank you a lot. Now I call upon the coordinator, Ms. G. Kalavati, to deliver the thank you note.
Good morning to Professor Jose. Good evening, everyone. It is a great pleasure for me to thank our distinguished speaker of Session 3 on behalf of the Organizing Committee, International E-Conference on Frontiers in Industrial Biotechnology. I wholeheartedly thank Professor Jose Antonio Teixeira for accepting our invitation to be plenary lecture and enlightening us with the information on clean and environmentally friendly technologies for the production of chemicals. I'm also thankful to you, Professor, for spending your valuable time with us. We are honored by your presence. And I thank all the participants for your kind cooperation throughout the session. Thank you all.
Okay, and once again, thank you for inviting me to be here. And anyone can, by the way, anyone can make use of this presentation. It's open to everyone. And if you have any doubts, please email me. Okay.
Thank you, Professor. Thank you very much. Thank you, Professor. Take care. Bye.
Okay. So.